So like I said, this is the globe of death, and then there's two stunts from this that we could use. The first one is a good review from the other day. And the other day we did the runner who did a loop, and he did a vertical loop. And even though you would think a vertical loop is harder, it's actually easier mathematically because we could kind of ignore friction. Friction's there because it's what's keeping the tires from slipping. But as it's doing the loop, it's not important that friction is present other than just making sure he doesn't slip, that the loop is possible. You could totally do the vertical loop without any friction. It's just more of getting the momentum started. So when we're looking at this is what we did the other day, and we're going to use the same numbers just to make life a little bit easier. So the runner had a mass of 75. So we'll kind of put that in. And from this, we know that what enable for this person to go around in a circle, there has to be a force or a sum of forces that's pushing towards the center. And we call this force, the sum of it, centrifugal force. And in order for it to keep in that circle, it always has to be pointing in the circle. Even over here, it's still pointing at the circle. It's just we don't analyze this corner is because you have to break apart the FG and FN into its angles, which is a pain. So we're just going to focus on the part where we don't have to. When you're looking at this, another thing that always holds true is force of gravity. FG is the same throughout the entire cycle or vertical loop. FG is mg. In this case, it's mass. So like I said, we're going to keep the same numbers. 75 times 10. So we're going to get 750. And even though it might not seem obvious, gravity never changes, because the Earth is always pointing us the same amount, and we don't change our mass in a motion. So in this case, it's always 750. Now, the bottom one kind of sucks because I can't draw it to scale because I'm out of room, but you get the point. All four situations, gravity is the same, negative 750. What's going to change is our centrifugal or force normal. On the sides, it's pretty straightforward. So this is the side. On the side, you have sum of all forces. In this case, is the x direction, and all you have is force normal, and that's it. There's gravity's in the vertical, and it's not on the same axis as FC, so we could ignore it. So force normal is equal to FC, and that's the only force providing centrifugal force. So that's true on both sides. On the top, though, sum of all forces in the y direction is equal to force of gravity and force normal, which will give us FC. So remember, sum of forces used to be MA, but since we're talking about centrifugal force, it's mv squared over r, because A is not changing in the way that we typically think of it. We're changing it angularly or directionally, so that's why it's v squared over r. Back to this, though. Force normal in this case is not the same as FC, but it's in complement with FG. FG plus FN has to give us FC. In our previous problem, we made FC equal to 800, so we kind of just have a visual of what's going on here. So if we do that, this is 750. Before I move on, FC here is down, FG is down, FN is down. So they're all the same signs. They're either all negative or all positive. It doesn't really matter. FC is negative 800. That's what we did the other day. So FN is 50, negative. So here, FN works with FG to create FC. On down here, FN has to be bigger than FC. And the reason is because at the bottom, sum of all forces in the y direction is still FG plus FN equals FC, but the difference this case is this is negative, FN's positive, FC is positive. The fact that FG and FC have opposite signs will make it different. So this is what we did on Friday of last week. And I want to reiterate that because I want to highlight that FC as it goes around, here it's only FN, here is both FG and FN, but they work together. Here they work against each other, so that's why FN's bigger. What happens now if we're moving sideways versus vertical? And when we do that, it might seem easier, but it gets a little bit more difficult because of a new force that's present. So here is my globe of death, vertical or horizontally. So if I show a video of it, let's see. So here you can see them moving in horizontal direction. They are not going up and down, but just moving horizontally. And we're going to look at the forces that are present as they do that. So let me get out of this screen, go back to the other one. So the globe of death. Now we're going to do only 2 of them just because it's easier to visualize. I'm going to skip the one in the back and the one in the front. But here you have 3 forces acting on the rider. You have force of gravity still. You have force normal. But you have one more force in order to keep this guy up. And that is force of static friction. Now, like I said, friction wasn't really necessary before because you were moving this direction. But now you're moving this direction. Some force has to keep it up because Fn isn't keeping you in the circular path. And some things keep fighting against gravity, and that has to be force of friction. Now, you might think, why is it even necessary? And it might not be, so let's set it up. Sum of all forces in the x direction is just still Fn, which will equal Fc. Now here, Fn is equal to something. Fc is mv squared over r. So, same as before, but here is the condition. If we look at the other side, sum of all forces in the y direction, you still have Fg plus force of static friction is equal to, I'm going to run out of room, but MA, let me change the color, MA. Now, you might not think this is significant, but if this doesn't equal 0, the rider is going to go up or down, but we want to make sure they stay in the middle, so that's why A is equal to 0. So in the trick, their velocity, their vertical position, does not change. So because they don't change, A is equal to 0. So that means force of gravity equals force of static friction. We're going to do absolute value because that's what we care about. And then the part that connects these 2 together is force of gravity is equal to mu Fn. So all of a sudden they're connected. The y and the x are connected because of friction. And if you could substitute that in, Fg is equal to mu mv squared over r. Now, Fg never changes. So that means as you increase velocity, the radius has to change in order for it to stay up, right? Or if you can't change anything, then it's not going to be equal to gravity, and then it's going to start sliding down. So there is a condition of this. There's a minimum velocity that you have to go in order to keep this circle. So if you want to solve for it, let's just change Fg to mg, mu mv squared over r. What's nice about all these problems is the mass always cancels out. Rg equals mu s v squared. So Rg mu s equals velocity. So this is the minimum speed that you have to go to in order to keep it moving. So that's a straight vertical. It's pretty nice, it's pretty easy. And now we're going to do the same thing, but we're going to do a horizontal turn. Any questions on this before I move on? Sorry, my screen is all messed up now. All right. So we're going to do a turn without a bank. Normally, when you're driving your car, when you see a turn, you're going to turn your wheels sideways. So instead of straight, they're going to be sideways. And you do that because you're going to create friction. That's going to be towards the middle of the road. Here's the center, and that's going to help you turn. The top view is a little bit easier to see. You have force normal, force of gravity, and then force of static friction. Sum of all forces in the x direction is once again force of static friction, which is equal to force of centrifugal force. And normally we'll just stop at that, right? You just plug it in, mu s Fn equals mv squared over r. And then that's when you actually have to relate, because friction always going to pull in Fn. In this case, it's nice and easy because it's not moving up or down. So sum of all forces in the y direction is Fg plus Fn, and they're equal to 0. So Fg is equal to Fn. It's a lot of work just to say that if this is negative mg, this one is positive mg. So you could just substitute that in. Mu s mg equals mv squared over r. Like I said, m always cancel out in these cases. R mu s equals, oops, I left one out. R mu s g equals v squared. So here's our first equation of the day. R mu s g. So if you want to find out how fast you can make a turn without a bank, this is the equation you use. So let's say I plugged in some stuff. The typical mu s for concrete and rubber is about 0.8. Let's say the radius here is 10 meters. So how fast can we make this turn? Well, you just plug it in. So velocity is equal to radius, in this case is 10. Mu s I said was 0.8. Let me make this cleaner. And then gravity will just be more accurate, so it's more obvious, 9.8, because I don't want to use two tens. 10 times 0.8 times 9.8. And I get a velocity of 8.85. So that means if mu s is 0.8, if the radius was 10, the fastest I could go making this turn is 8.85 meters per second. If I go any faster, I'm going to skid out of control. So that's in the movie. They're making a turn and then they're too fast, so the car starts sliding out. Any questions so far? Okay, I lost all camera. I don't see anybody's camera. So
What happens if you go slower than
if you go slower, it's okay because you have more force of friction than you need. So if you're going slower, you can make the turn perfectly fine.
Oh, why do you have more friction if you go slower?
Because friction is based on Fn, right? Force of static friction max is mu s Fn. So this doesn't change, right? So this will be based on this right here. So since this doesn't change, you're going to have a fixed number. If you go bigger than this, you're going to lose control. But if you're under than this, you always have enough friction to make that turn.
Okay, I see.
So we're not on a bank yet. So once you're on a bank, it's going to change just a little bit. But right now we're on a flat turn. All right, so a bank turn helps us go through a corner much, much faster. So here we kind of have an example of a velodrome. It's really cool if you've ever ridden on one. Here is the reason why you have velodrome is you have a track. You have bikes that could go up to 40, 50 miles per hour, so track cyclists could get up to those speeds. At those speeds, you can't really make a turn, right? So what they do is to help them out is they angle the corners. Right here is 45 degrees. So if they're going fast, they could get up on the corner. And with that, force normal is going to help them make the turn very similar to this, but just not this extreme. So we're going to look how much a bank turn can help us. So here you have 12 degrees, 45. If you ever watch NASCAR, that oval, it's on a bank turn, and that's why they're able to go that fast, is because of that bank. All right, so just like I said, this is going to get kind of ugly. Don't worry about the math to get there. The main thing is I want to show you how I get the final product or how I got the formula. All right, the goal is to find FC. what forces provide Fc. In this case, there are going to be two. So the first one we're going to do is without, whoops, I could spell, without friction. So it makes it a little bit easier just handling one at a time. So Fc is this direction. And because it's that direction, I'm going to make this my frame of reference, meaning that I'm going to define my x and y based on Fc, because that's the one I care about. So if that's true, I'm going to draw a reference x and y for myself. Here's a reference x. It looks horizontal, kind of. Yeah, good enough. And here's a reference y. So here's my y, here's my x. The reason is because I want it to be related to Fc. There's going to be two forces acting on it. There's going to be force of gravity. And gravity is going to be straight down. Let me choose a better color. And this is force of gravity. And it's straight down. And then the next force that we have is force normal. And this one is perpendicular to the ground. So more like that. So here are my two forces. The only thing I care about is any force in the x direction. Fg is only in the y, so Fg is not involved. So what it's involved is breaking apart Fn into its components. Here is force normal in the y, and then you have force normal in the x. So for us, that's the one of concern. So sum of all forces in the x direction is equal to force normal in the x, which is equal to Fc. You're like, hey, that's simple enough. So let's read it. But then you realize, oh wait, I have no idea what force normal in the x is. So then you go, okay, well, I do know angles. This angle's here, this angle's here. So I'm going to do some trig identities. So sine of theta is opposite Fnx over Fn. So opposite over hypotenuse. And so that means force normal is equal to, force normal times sine theta is equal to force normal in the x direction. So I'm going to plug that in over here. Force normal in this times sine theta equals mv squared over r. Now here's the second problem. All right, you go, okay, Fn is normally Fg, but it isn't here. Right, Fg is not opposite direction of Fn. Fg is the opposite direction of Fny. Like, great. Okay. So what you're going to do is if you have this, sum of all forces in the y, you have Fg plus Fny equals Ma. Since it's not moving up and down, Ma is 0. So pretty much the absolute value of Fg is equal to the absolute value of Fny. Now you go, okay. That's not useful in this equation, so I'm going to have to use my other trig identity. Cosine theta is equal to adjacent Fny over Fn. So Fn is equal to, whoops, I did it again. Fn cosine theta is equal to Fny. So I'm going to substitute that over here. Fg is equal to Fn cosine theta. But I want to substitute this thing out, so I'm going to move this to the other side. Mg, which is Fg, divided by cosine theta equals Fn. And you're like, okay, now I'm going to substitute this over here. So Mg cosine theta, because it's equal to Fn, times sine theta equals mv squared over r. And now you're done. You have an equation with things that you like: mass, gravity, angle, radius. The mass, again, always cancels out. So you're just left with g. I'm going to combine sine and cosine together. Tangent theta is equal to v squared over r. Move the r over. Rg tangent theta is equal to v squared. But I'm just going to take the square root. So here is our first equation, or second equation. The first one is with friction, But flat, this one is bank turn, but without friction. So if you have a bank turn and you didn't have any friction, you can still make a turn. Here it is. The radius is what it is. You have gravity and tangent of an angle. So you could do it even without it. Questions on this one? All right. The last one's going to be the ugliest one. So like I said, don't freak out how ugly it's going to get. Just know that I'm going to come up with an equation at the end for us to use. So that's our second one. And I already did screenshots and I'll post it up on our websites or Google Classroom. So now I'm going to do the same thing, but I'm going to do it with friction. So just bear with me. I'm going to talk less because I just want to show you once again, we only care about the forces in the x direction, but eventually we're going to pull in the y force, y, because of force of friction. But in this case, we're going to have three things. We still want to use the frame of reference like before. So here's still my x and here's still my y. And I'm going to base everything off of those two. Gravity is still this way. So here's gravity. I'm still going to have the same normal. Let me choose a darker color this time. Same normal. But now we're going to have force of friction. And force of friction is going to be parallel to the surface. Like that. So this should be parallel, this should be a right angle to surface, and this should be straight down. No, I will never make you guys memorize how to derive it. I just like to show you where I get them. So I hate just giving you random formulas. So I like showing it even though I don't need you to memorize how to get there. All right. Like before, we want to break it down because the only ones we care about are the ones in the x direction. So for this one, you have force normal in the y, force normal in the x, and then you're going to break apart friction the same way. You have force of friction in the x, force of friction in the y. Now these frictions are static. I'm just going to drop the static just because it'll keep my math a little bit easier. I know eventually I'm going to need the sine identities of all these, sine and cosine, so I'm going to do it over here. So opposite over hypotenuse. Now I'm going to do the same thing with cosine. Adjacent. Do the same thing with friction. So opposite is Fm is force of friction y, force of friction. And then the last one is cosine. So I'm doing this ahead of my work just because I know I'm going to use them all. Force of friction x. Oops. All right, so I have all my identities here. I'm going to set up my two sum of all forces. Sum of all forces in x is equal to 1, 2 forces. Force normal x plus force of friction x. I believe that's it. Yep. And that's equal to force of centripetal. We do the same thing with y. Y, we have more. We have force normal y plus Fg plus force of friction y. Now, the part that you really need to make sure is that the signs are correct. For the x, they're all in the same direction. To the left, to the left, to the left. So all these are going to be either all negative or all positive. So to be honest, it doesn't matter. We just care about in relationship to each other. So if you make them all negative, all positive, it's still going to give you the right answer. This is not. F and y is up, while fg and ffy is down. So whatever you do, you just need to remember that these are going to be different signs than this one. So if you make this one positive, these are negative. If you make this one negative, these are positive. The sum of all forces is 0 because the car is not moving up or down. It's only going in a circle. So here's my 2. I'm going to somehow combine these two to come up with my final equation. And I'll kind of show why we have to combine it. With the x first. Fnx is right here, which is Fn sine theta. So I'm just substituting the trig. Ffx is this one right here, Ff cosine theta. And this is equal to mv squared over r. So we're getting closer. I'm going to redefine force of friction. And we're kind of at the same place again. Force normal is not mg. Sucks. Okay. It is something else. So what I'm going to do is I have to use this, solve for this one, substitute it in. Before I do that, I'm going to pull out Fn to make it a little bit easier. So all right, so now I'm going to go on this side, solve for Fn so I could substitute it in here. Fny is Fn cosine theta. F of g is mg. And then Ffy is force of friction sine theta. Okay. Now, like I said, sine, this is negative, so I'm going to rewrite it with that. Fn cosine theta minus mg minus mu fn sine theta equals 0. Ooh, 0. Okay.
Mr. Singh?
Yes.
Why is force of friction negative?
Because when we're drawing it with my x and y, friction right here is parallel to the ground. So when you break it apart into its x and y component, the x is this way, and then its y is down because it's angled with the surface. So it's negative because we're comparing it to each other. So if gravity is negative, this one's negative because these vectors are pointing the same direction. Force normal is pointing up, so it's going to be positive. Kind of like what I said here. It doesn't really matter which one's negative or positive. Just make sure that in relationship to each other, they're correct. So if you make this one negative, these two have to be positive. If you make this one positive, these two have to be negative. And that's it. In relationship to each other, they have to be correct. Does that make sense?
Yes. And one more question. Why is force of friction pulling the car sort of downwards? I thought force of friction would sort of, keep the car or prevent it from going downwards because there's like, friction.
So if this thing wasn't moving, or turning, then force of friction is actually going to be the other direction because gravity is going to be pulling the car technically down the plane. Now, in this case, we're actually making a turn. And the thing that's helping us make the turn is friction. So you have to go back to our previous problem where it's a flat turn and the thing that's making you turn is force of friction. So friction is making you turn, but another force is helping us now making that turn, which is force normal. So we're including both of these.
Friction helps you make the turn.
Yeah,
okay.
So just imagine when it's flat, when you turn your wheel, that's what's making you turn, the friction between your wheels and the ground. If you didn't have any friction, then it's like ice, right? You turn the wheel on ice. If you ever hit black ice before, you just slide forward. All right, kind of back to this. We're almost done. So bear with me. The math is almost over. Let's see. Where was I? Oh, yeah. So I replaced force of friction to mu Fn. Now my goal is to isolate Fn so I can substitute it in here. So I'm going to move mg to the other side of the equation and put these together. So I have Fn cosine theta minus mu Fn sine theta equals mg. I'm going to factor out fn, cosine theta minus mu sine theta equals mg. Now I'm going to move this over to the other side. So fn is equal to mg divided by cosine theta minus mu sine theta. Ooh, all done. So now I have two equations with fn. I'm going to substitute one in. So I'm going to take this thing, going to move it over to the other side. So mg cosine theta minus mu sine theta times our original sine theta plus mu cosine theta equals mv squared over r. So as before, m's always cancel out. My goal is to isolate v, so I'm going to multiply the other side by r. So you get rg times sine theta plus mu cosine theta divided by cosine theta minus mu sine theta equals v squared. And then to get rid of the squared, you take the square root. So here is my last equation, and it's pretty ugly, but there it is. Now, if you look at what I posted online as well, I also posted this website. So this person took it another step further. So after deriving what we just did, they did the right here. If you look right here, they did sine or trig identities to change it to tangent. If that's what you prefer, that's fine. In the normal class, we have a cheat sheet. In this one, you could always just look up what I write here. So you never have to memorize this for me. I'm pretty sure no professor will ever make you memorize this. This is something that you just Google and look up the equation for. But that's how you get it. It's pretty nasty, but there we go.